come along. It's time to learn and sing our song. With fun and games, we'll play all day and learn new things along the way. We'll count the stars and dance in rain. We'll find adventures in every lane. With laughter bright and hearts so wide, on this journey we'll take pride. Let's explore the world so grand, with magic in our hands. Through fields of dreams we'll boldly roam. Together we'll call this place our home.
Hey guys! Welcome to our fascinating exploration of the planet Mercury, the smallest and closest planet to the Sun in our solar system, a mysterious and extreme world that has captivated scientists and stargazers alike for centuries. In this video, we'll dive deep into what makes Mercury so unique, from its scorching daytime temperatures that can soar to a blistering 430 degrees Celsius, 800 degrees Fahrenheit, to its freezing nights that drop to an unimaginable minus 180 degrees Celsius, minus 290 degrees Fahrenheit, showcasing the most extreme temperature fluctuations of any planet due to its lack of a substantial atmosphere to regulate heat. As the fastest orbiting planet, completing a journey around the Sun in just 88 Earth days, yet spinning slowly on its axis with a day lasting nearly 59 Earth days, Mercury presents a fascinating paradox of speed and stillness, which has puzzled astronomers and inspired countless studies. We'll uncover its rugged and cratered surface that bears a striking resemblance to the Moon, featuring massive impact basins like the awe-inspiring Caloris Basin, towering cliffs called scarps formed by the planet's contraction, and ancient volcanic plains that tell a story of a geologically active past. We'll also delve into its surprisingly large metallic core, which dominates 85% of the planet's radius and gives rise to a magnetic field, an unexpected discovery for a planet of its size, providing a glimpse into the complex processes at work beneath its surface. Mercury's incredibly thin exosphere, composed of hydrogen, helium, oxygen, and other elements, adds another layer of intrigue, constantly replenished by solar wind and micrometeoroid impacts, highlighting its dynamic interaction with the Sun. Despite its proximity to the Sun, Mercury has no moons or rings, and its position makes it one of the most challenging planets to observe from Earth, visible only during brief moments at dawn or dusk. We'll also touch on humanity's efforts to unravel Mercury's secrets, from NASA's historic Mariner 10 mission and the groundbreaking discoveries of the Messenger spacecraft, which orbited the planet for years, to the ongoing BepiColombo mission, which promises to revolutionize our understanding of this enigmatic world. Whether you're a space enthusiast curious about Mercury's role in the solar system, a student eager to learn about its scientific significance, or simply fascinated by the wonders of space, this video will take you on a journey through the extreme, mysterious, and captivating world of Mercury, a planet that challenges our understanding of planetary science and offers endless opportunities for discovery and wonder. Now let's begin our studies. Mercury holds the position as the innermost planet in the solar system, making it the closest planet to the Sun, a defining characteristic that profoundly influences its environment, orbit, and role within our planetary family. As the first planet from the Sun, Mercury orbits at an average distance of 0.78 astronomical units, approximately 58 million kilometers, 36 million miles, a mere fraction of the distance between the Sun and Earth, placing it in an extreme location where solar radiation and gravitational forces dominate its existence. This proximity to the Sun gives Mercury an orbit that is the fastest of all the planets, taking just 88 Earth days to complete one revolution, a feature that earned it the nickname of the Swift Planet, inspired by its rapid motion across the sky as observed by ancient civilizations. Its elliptical, oval-shaped orbit adds complexity to its movement, with Mercury coming as close as 46 million kilometers, 29 million miles, to the Sun at its perihelion, and as far as 70 million kilometers, 43 million miles at its aphelion, leading to variations in the amount of solar energy it receives and contributing to the planet's extreme temperature fluctuations. Unlike the outer planets, which often have thick atmospheres to moderate temperatures, Mercury's position so close to the Sun means it has lost most of its atmosphere due to the Sun's intense radiation and solar wind, leaving it with a tenuous exosphere that is constantly replenished by particles from the sun and micrometeoroid impacts. The lack of a substantial atmosphere also means that Mercury experiences some of the most dramatic temperature extremes in the solar system, with its dayside reaching scorching highs of 430 degrees Celsius, 800 degrees Fahrenheit, and its nightside plunging to freezing lows of minus 180 degrees Celsius, minus 290 degrees Fahrenheit, a direct result of its position near the sun combined with its inability to retain heat. Mercury's location also subjects it to powerful gravitational interactions with the sun, which have shaped its unique rotational characteristics, such as its 3-to-2 spin-orbit resonance, where the planet rotates 3 times on its axis for every 2 orbits around the sun, causing a single day, sunrise to sunrise, on Mercury to last 176 Earth days, a phenomenon that results in an unusual interplay of day and night on its surface. Being the closest planet to the sun also means that Mercury lacks any natural satellites or rings, as the sun's strong gravitational pull would destabilize any such structures, further emphasizing its stark, solitary nature as it orbits in the inner sanctum of the solar system. Despite its extreme position, Mercury plays a crucial role in our understanding of planetary formation and dynamics, as its proximity to the sun provides scientists with insights into the effects of solar radiation, gravitational tides, and extreme thermal conditions on planetary bodies, making it a key focus for missions like Mariner 10, Messenger, and BepiColombo, which aim to uncover the secrets of this enigmatic planet that orbits closest to the fiery heart of our solar system. Mercury, the closest planet to the sun, has unique orbital characteristics that distinguish it within the solar system. It orbits the sun at an average distance of approximately 57.91 million kilometers, 36 million miles, making it the innermost planet, and completes one orbit in just 88 Earth days, due to its high orbital velocity of about 47.87 kilometers per second, 29.74 miles per second, the fastest of any planet. Mercury's orbit is highly elliptical, eccentric, with an eccentricity of 0.2056, meaning its distance from the sun varies significantly, ranging from about 46 million kilometers, perihelion, to 70 million kilometers, aphelion. This elliptical orbit, coupled with its proximity to the sun, causes variations in Mercury's solar insolation and surface temperatures, with extreme fluctuations between daytime highs exceeding 430 degrees Celsius, 800 degrees Fahrenheit, and nighttime lows plunging to negative 180 degrees Celsius, negative 290 degrees Fahrenheit, because of its thin atmosphere, which cannot retain heat. Mercury's axial tilt is almost negligible at 0.034 degrees, the smallest of any planet, which means it experiences no significant seasonal variations. Its rotation period, or sidereal day, is approximately 59 Earth days, which creates a fascinating 3-to-2 spin-orbit resonance. The planet rotates 3 times on its axis for every 2 orbits around the sun. This resonance results in an unusual day-night cycle, with a solar day, the time from one sunrise to the next, lasting about 176 Earth days. Mercury's orbit also exhibits precession, where the perihelion of its orbit shifts over time. This phenomenon was famously explained by Einstein's general theory of relativity, offering key evidence for the theory. Its proximity to the sun and orbital characteristics also contribute to intense gravitational interactions, leading to tidal locking effects that stabilize its spin-orbit relationship over time. These orbital and physical attributes make Mercury a subject of considerable interest in planetary science and astronomy. Mercury experiences some of the most extreme temperature variations in the solar system due to its unique position, lack of atmosphere, and orbital and rotational characteristics, making it a fascinating subject for study. As the closest planet to the sun, Mercury receives intense solar radiation, causing its surface temperatures during the day to soar to an astonishing 430 degrees Celsius, 800 degrees Fahrenheit, in regions directly exposed to sunlight, making it one of the hottest places in the solar system. This extreme heat is primarily because Mercury has virtually no atmosphere to block or scatter the sun's radiation, allowing sunlight to hit the surface directly and intensely. Unlike Earth, which has a thick atmosphere capable of distributing heat across the planet and moderating temperatures. Mercury's exosphere, a tenuous layer of gases composed mostly of hydrogen, helium, sodium, and potassium, is so thin that it cannot retain heat or redistribute it effectively. This lack of an insulating atmosphere also explains the drastic drop in temperatures during the night. As soon as the sun sets, the surface rapidly loses heat into the vacuum of space, plunging to frigid lows of approximately minus 180 degrees Celsius, minus 290 degrees Fahrenheit, colder than any temperatures experienced on Earth. Compounding these extremes is Mercury's unique day-night cycle, dictated by its 3-to-2 spin-orbit resonance, where it rotates on its axis 3 times for every 2 orbits around the Sun, resulting in a solar day from one sunrise to the next that lasts about 176 Earth days. This prolonged exposure to sunlight during the day and the equally extended period of darkness at night exacerbate the temperature swings. Furthermore, Mercury's highly elliptical orbit, with distances from the Sun ranging between about 46 million kilometers, perihelion, and 70 million kilometers, aphelion, means that the intensity of sunlight it receives can vary significantly, adding another layer of complexity to its thermal environment. These extreme temperatures, combined with the planet's thin exosphere and prolonged day-night cycle, make Mercury a uniquely harsh and inhospitable world, providing scientists with a natural laboratory to study planetary behavior under conditions vastly different from those on Earth. Mercury's surface features are a fascinating tapestry of geological formations that tell the story of a small, dense, and ancient planet shaped by intense impacts, volcanic activity, and tectonic forces over billions of years. Dominated by craters, Mercury's surface resembles that of Earth's moon, marked by countless impact craters formed from collisions with asteroids and comets during the early history of the solar system, particularly during the late heavy bombardment about 4 billion years ago. One of the most prominent surface features is the Caloris Basin, a colossal impact crater spanning approximately 1,550 kilometers, 960 miles, in diameter, making it one of the largest impact structures in the solar system. This basin is surrounded by concentric rings of mountains and is filled with smooth plains likely formed by volcanic activity that followed the initial impact. Mercury's surface is also crisscrossed by a network of long, steep cliffs known as scarps, some extending hundreds of kilometers and rising up to 3 kilometers, 1.9 miles, high, which were formed as the planet cooled and contracted over time, causing the crust to shrink and crack. These scarps provide evidence of Mercury's tectonic activity and its slow cooling process. Interspersed among the craters are smooth plains, both older intercrater plains and younger, sparsely cratered plains that suggest widespread volcanic resurfacing events in the past, although active volcanism no longer occurs on Mercury today. The planet's surface is covered by a thin layer of regolith, a mix of dust and fragmented rock created by continuous micrometeoroid impacts, which gives Mercury its grayish, weathered appearance. Another intriguing feature of Mercury is the presence of hollows, bright, shallow depressions found in some craters, likely formed by the sublimation of volatile elements exposed by impacts, a process unique to Mercury in the inner solar system. Mercury's surface also contains evidence of past magnetic field activity, with areas of remnant magnetization detected in rocks, pointing to a time when its dynamo-generated magnetic field was much stronger. The absence of an atmosphere means that surface features remain largely unchanged over billions of years, as there is no wind, rain, or tectonic plate activity to erode or reshape them. Additionally, Mercury's surface experiences extreme temperature variations, contributing to thermal stress that may influence the development of some features. Together, these diverse geological characteristics make Mercury a planet of contrasts, reflecting a dynamic early history followed by a long period of quiescence, providing valuable insights into planetary formation and evolution. Mercury's atmosphere, or more accurately its exosphere, is an exceptionally thin and tenuous layer of gases that sets it apart from the robust atmospheres of planets like Earth or Venus. And its composition, origin, and behavior are key to understanding the unique environment of the closest planet to the Sun. Unlike a traditional atmosphere held in place by significant gravity and capable of weather systems, Mercury's exosphere is so sparse that it cannot trap heat or support any atmospheric pressure, making it more akin to a vacuum than a true atmosphere. Composed primarily of hydrogen, helium, oxygen, sodium, potassium, and trace amounts of other elements, Mercury's exosphere is constantly replenished by a combination of processes, including solar wind bombardment, micrometeoroid impacts, and the thermal desorption of volatile materials from its surface. The sun's intense radiation plays a critical role in this dynamic system as particles from the solar wind, traveling at high velocities, collide with Mercury's surface, knocking atoms off the planet's crust in a process known as sputtering. Micrometeoroid impacts further contribute by vaporizing small amounts of surface material, releasing elements into the exosphere. Additionally, thermal desorption occurs as the planet's extreme daytime temperatures cause some surface-bound particles to gain enough energy to escape into the exosphere. Mercury's exosphere is also influenced by its weak magnetic field, which interacts with the solar wind, creating localized regions where particles are funneled to or stripped away from the surface. Sodium and potassium, two prominent components of Mercury's exosphere, produce a faint yellowish glow detectable by spectroscopic instruments, offering scientists clues about the planet's surface composition and the processes that sustain the exosphere. The exosphere is not uniform. Its density and composition vary based on the planet's location in its highly elliptical orbit, as well as the time of day, with daytime exposure to the sun driving the most significant release of particles. Despite its thinness, Mercury's exosphere is a dynamic system in constant flux, shaped by its proximity to the sun and its geological and magnetic properties. This fragile envelope of gas cannot shield the surface from the sun's radiation or retain heat, contributing to the planet's extreme temperature fluctuations. Mercury's exosphere represents a fascinating intersection of geology, solar physics, and planetary science, providing a unique laboratory for studying how atmospheres and exospheres behave under the harsh conditions of the inner solar system, where proximity to a star profoundly influences planetary environments. Mercury, the smallest planet in our solar system, has a unique and intriguing internal structure that has fascinated scientists for decades. Its composition provides insights into the processes that shape the terrestrial planets. Mercury's interior consists of three primary layers: a metallic core, a silicate mantle, and a thin crust. The most distinctive feature of Mercury's internal structure is its extraordinarily large core, which constitutes about 85% of the planet's radius, a far greater proportion compared to Earth, Venus, or Mars. This core is believed to be predominantly composed of iron, with smaller amounts of nickel and potentially lighter elements such as sulfur. Seismic and gravitational data suggest that Mercury's core is partially molten, with an outer liquid layer surrounding a solid inner core, much like Earth's. This liquid outer core is thought to drive Mercury's weak magnetic field, which is unique among terrestrial planets other than Earth. Surrounding the core is the mantle, a rocky layer that is surprisingly thin compared to those of other terrestrial planets, measuring roughly 400 kilometers in thickness. The mantle is composed of silicate minerals, and its formation involved processes of melting and differentiation during the planet's early history. Evidence of ancient volcanic activity on Mercury's surface suggests that heat from the mantle played a role in shaping the planet's crust. The outermost layer, the crust, is estimated to be about 35 kilometers thick and is primarily composed of silicate rocks. Mercury's crust exhibits extensive tectonic features, such as scarps and ridges, which likely formed due to the cooling and contraction of the planet over billions of years. Interestingly, Mercury's high density, second only to Earth among the planets, implies that it lost much of its original rocky material early in its formation, possibly due to a giant impact or proximity to the Sun during the planetesimal accretion phase. This disproportionate loss of lighter materials further accentuates the dominance of its metallic core. Additionally, Mercury's proximity to the Sun means it has been heavily bombarded by solar wind particles, influencing its exosphere and contributing to the evolution of its surface and internal structure. Studies of Mercury's interior continue to advance with data from missions like NASA's Messenger and ESA's BepiColombo, which aim to unravel the mysteries of its formation, thermal evolution, and current state. Understanding Mercury's internal structure not only sheds light on its unique characteristics, but also provides a broader context for studying planetary formation and differentiation in the inner solar system, offering valuable comparisons with Earth and other terrestrial planets. Day and night on Mercury are phenomena that highlight the planet's unique position and rotation within our solar system, creating an extreme and fascinating contrast in environmental conditions. Unlike Earth, where day and night occur every 24 hours due to its rapid rotation, Mercury experiences a day-night cycle that spans much longer because of its unusual rotational dynamics and orbital period. Mercury rotates on its axis very slowly, taking approximately 59 Earth days to complete one rotation. At the same time, it has a highly elliptical orbit around the Sun, completing a single revolution in just 88 Earth days. This combination of slow rotation and fast revolution leads to a situation known as a 3-to-2 spin-orbit resonance, meaning Mercury rotates exactly 3 times on its axis for every 2 orbits around the Sun. As a result, a single solar day on Mercury, defined as the time it takes for the Sun to appear in the same position in the sky from the planet's surface, lasts about 176 Earth days, which is twice as long as its year. This extended day-night cycle creates some of the most extreme temperature variations in the solar system. During the day, when Mercury's surface is exposed to the Sun's intense radiation, temperatures soar to an astonishing 430 degrees Celsius, 800 degrees Fahrenheit, hot enough to melt lead. Mercury has no substantial atmosphere to distribute heat or provide insulation, so the heat remains localized to the sunlit side. Conversely, during the night, when the Sun is no longer visible, surface temperatures plummet to a frigid minus 180 degrees Celsius, minus 290 degrees Fahrenheit, as any stored heat quickly radiates away into space. This extreme dichotomy between the scorching day and freezing night is further accentuated by the planet's lack of an atmosphere, which on Earth helps moderate temperature differences. Adding to the complexity of Mercury's day-night experience is its sky viewing phenomenon. Due to its eccentric orbit, an observer standing on Mercury's surface would see the Sun exhibit peculiar motions during sunrise and sunset. In some regions, the Sun appears to rise, slow down, briefly reverse its course, and then resume its path across the sky, a result of the interplay between Mercury's orbital velocity and rotational speed. Similarly, sunsets display the same backward movement before the Sun sinks below the horizon. These unusual motions are due to the significant variations in Mercury's orbital speed as it travels along its elliptical path. It moves faster when closer to the Sun, perihelion, and slower when farther away, aphelion. Moreover, the extended duration of Mercury's daytime means that sunlight continuously heats the surface, causing rocks and regolith to expand slightly, while the prolonged nighttime allows ample time for them to contract, potentially contributing to the development of surface features like cracks and ridges. This cycle of thermal stress plays a significant role in shaping Mercury's landscape over billions of years. The stark contrast between day and night also affects the planet's exosphere, a tenuous layer of atoms and particles that are ejected from the surface by solar wind and micrometeoroid impacts. During the day, solar radiation enhances the activity of these processes, while at night, the absence of sunlight allows some particles to settle back onto the surface or escape into space. In summary, day and night on Mercury are defined by an extraordinary interplay of its slow rotation, elliptical orbit, and proximity to the Sun, creating a world of extremes where time flows differently. Temperatures reach staggering highs and lows, and the Sun performs celestial dances unlike anywhere else in the solar system. This unique environment has not only shaped Mercury's surface and geological history, but also provides scientists with a deeper understanding of planetary behavior under extreme conditions, offering a glimpse into the dynamic processes that govern other celestial bodies within and beyond our solar system. The lack of moons or rings around Mercury, the smallest and innermost planet in our solar system, is a subject of significant scientific interest that reflects its unique position and history in the solar system. Unlike planets such as Jupiter and Saturn, which boast extensive systems of moons and rings, or even Earth, which has a single natural satellite, Mercury stands out as a starkly isolated body with no known natural satellites or ring systems. This absence is primarily attributed to several key factors related to Mercury's proximity to the Sun, its size, gravitational dynamics, and evolutionary history. First and foremost, Mercury's location near the Sun plays a critical role in its inability to retain moons or develop a ring system. The Sun's immense gravitational pull dominates the region around Mercury, exerting a tidal force so strong that any potential moon would either be drawn into the Sun or pulled away from Mercury entirely. This means that if Mercury ever had a moon in its distant past, it would have faced immense difficulty maintaining a stable orbit due to the overpowering influence of solar gravity. In addition, Mercury's small size and low mass significantly limit its gravitational influence. With a diameter of just 4,880 kilometers and a mass only about 5.5% that of Earth, Mercury's gravitational field is relatively weak compared to other planets. This limited gravity reduces its ability to capture or retain objects in orbit, such as stray asteroids or debris that could coalesce into a moon or contribute to a ring system. For example, larger planets like Jupiter or Saturn, with their immense gravitational pull, can easily capture smaller objects and sustain them as moons or ring material, but Mercury lacks this capability. Similarly, the weak gravitational field means that collisions with asteroids or comets, which could theoretically produce debris sufficient to form a ring system, are unlikely to result in long-lived orbital structures. Instead, such debris would either fall back onto Mercury's surface or escape into space, further explaining the absence of rings. The lack of moons or rings around Mercury is also a consequence of its formation and early history. Scientists believe that the inner solar system was a chaotic and violent environment during Mercury's formation over 4.5 billion years ago. Early collisions with other protoplanets or planetesimals likely played a role in shaping Mercury's current composition and size. If Mercury ever had moons or rings, they could have been destroyed or ejected during these early impacts. For example, a giant impact, similar to the one thought to have formed Earth's moon, might have stripped Mercury of its outer layers and any nascent moons or potential ring-forming material, leaving it barren. This scenario aligns with Mercury's anomalously large metallic core, which suggests it lost much of its original rocky material, possibly through catastrophic events. Moreover, Mercury's proximity to the Sun exposes it to intense solar radiation and the effects of the solar wind, a constant stream of charged particles emitted by the Sun. This harsh environment further reduces the likelihood of maintaining a ring system. Any fine particles that might form rings would be quickly eroded or pushed away by the solar wind and radiation pressure, preventing the accumulation of stable ring material. Similarly, the high-energy environment near the Sun increases the rate of sublimation and erosion for small icy or rocky bodies, further diminishing the chances of long-term moon or ring formation. Finally, the absence of moons or rings around Mercury might also be tied to the planet's relatively low angular momentum. Moons and rings often form as a result of the redistribution of angular momentum in a planet system, either through the capture of external objects or the accretion of debris from the planet itself. However, Mercury's slow rotation, with a rotational period of 59 Earth days, and its relatively small mass, imply that it lacks the necessary angular momentum to support such processes effectively. In summary, the lack of moons or rings around Mercury is the result of its unique combination of factors. Its proximity to the Sun and the overpowering solar gravitational forces, its small size and weak gravitational field, the chaotic conditions of its formation and history, and the intense solar radiation and wind that continuously affect its environment. This stark isolation makes Mercury an outlier among the planets in our solar system, offering a valuable perspective on the diversity of planetary systems and the myriad factors that influence their development. By studying Mercury's barren state, scientists gain deeper insights into the dynamics of planetary evolution, the role of solar proximity, and the processes that determine whether a planet can sustain satellites or ring systems over billions of years. Hey there! If you're enjoying this so far, don't forget to like this video and subscribe to our channel. It really helps us out and keeps you updated with all our latest content. Hit that notification bell so you don't miss a thing. Let's keep going! Mercury, the innermost planet of our solar system, holds a profound historical significance that spans across human observation, scientific discovery, and our evolving understanding of planetary science. Its visibility from Earth has made it a prominent figure in human culture for thousands of years, with records of its existence found in ancient civilizations such as the Sumerians, Babylonians, Greeks, and Romans. The Sumerians, as early as the 3rd millennium BCE, documented Mercury's movement, associating it with the god Nabu, the deity of wisdom. The Babylonians called it Nebu, while the Greeks recognized its dual appearances, visible both at dawn and dusk, and named it Apollo when it appeared in the morning and Hermes in the evening, reflecting its swift motion across the sky. This duality contributed to the mythology surrounding Mercury as a messenger, a theme that persisted in Roman mythology, where the planet was named after the god Mercury, known for his speed and agility. Its rapid motion against the backdrop of stars fascinated ancient astronomers, who worked to understand its complex orbital patterns and elusive visibility due to its proximity to the Sun. As astronomy advanced, Mercury became a critical puzzle in the development of heliocentric models of the solar system. Copernicus's revolutionary model placed Mercury closest to the Sun, and its movements provided key observational challenges that were later addressed by Kepler's laws of planetary motion and Newton's laws of gravitation. Mercury's perihelion precession, its gradual shift in the closest point of its orbit to the Sun, posed a mystery that classical mechanics could not fully explain, eventually becoming a cornerstone for Albert Einstein's general theory of relativity. Einstein's calculations showed that the curvature of spacetime caused by the Sun's immense gravity accounted for the anomalous precession of Mercury's orbit, providing one of the first experimental validations of the groundbreaking theory. This highlighted Mercury's unique role in bridging classical and modern physics. In the modern era, Mercury has served as an invaluable subject for planetary exploration and scientific inquiry. Its surface, marked by craters, cliffs, and plains, offers a window into the early history of the solar system, preserving evidence of processes like accretion, differentiation, and bombardment that shaped terrestrial planets. Missions like NASA's Mariner 10 in the 1970s provided the first close-up images of Mercury, revealing its heavily cratered terrain and magnetic field, a surprising feature for such a small planet. Decades later, the MESSENGER mission vastly expanded our understanding, mapping the entire surface, studying its thin exosphere, and uncovering the presence of water ice in permanently shadowed craters at its poles, an astounding discovery given Mercury's proximity to the Sun. These findings have positioned Mercury as a key comparative planet, allowing scientists to test hypotheses about planetary formation, magnetic field generation, and surface evolution. Beyond its scientific importance, Mercury also holds cultural and symbolic resonance, often representing swiftness, adaptability, and the passage of time in literature, art, and astrology. Its unique characteristics and historical significance make it not only a vital subject in astronomy, but also a testament to humanity's enduring curiosity and quest for knowledge about the cosmos. Through centuries of observation and exploration, Mercury continues to enrich our understanding of the universe and our place within it, embodying the interconnected history of human thought, science, and discovery. The exploration of Mercury, the innermost planet of our solar system, represents a fascinating chapter in the history of space science, marked by technological innovation, scientific breakthroughs, and the pursuit of understanding one of the most enigmatic terrestrial planets. Despite its proximity to Earth, Mercury's exploration has been remarkably challenging due to its closeness to the Sun, which creates extreme thermal conditions, intense solar radiation, and significant gravitational pull that complicate mission design. Early efforts to understand Mercury were limited to telescopic observations, with astronomers noting its elusive behavior as it remained visible only during brief windows at dawn and dusk. These observations revealed Mercury's rapid orbital motion and phases similar to those of Venus, sparking curiosity about its physical and orbital characteristics. The breakthrough in Mercury exploration came with the advent of space-age technology in the mid-20th century. NASA's Mariner 10 became the first spacecraft to visit Mercury, launching in 1973 and conducting 3 flybys of the planet between 1974 and 1975. Using the gravitational pull of Venus for a trajectory adjustment, Mariner 10 was able to make groundbreaking observations, capturing the first close-up images of Mercury's surface and revealing a heavily cratered terrain reminiscent of Earth's moon. This mission provided critical insights into Mercury's exosphere, magnetic field, and lack of a substantial atmosphere, laying the foundation for future exploration. Following Mariner 10, decades passed without a dedicated mission to Mercury due to the immense technical and financial challenges of reaching and studying the planet. However, renewed interest in planetary science led to the development of NASA's MESSENGER, Mercury Surface, Space Environment, Geochemistry, and Ranging mission, which launched in 2004 and became the first spacecraft to orbit Mercury in 2011. Over its 4-year orbital mission, MESSENGER revolutionized our understanding of Mercury by mapping its entire surface in unprecedented detail, studying its thin, dynamic exosphere, and confirming the presence of water ice and organic compounds in permanently shadowed craters at its poles. These findings were particularly surprising given Mercury's extreme temperatures and proximity to the Sun, providing evidence of complex interactions between solar wind, surface materials, and the planet's unique geological and magnetic history. MESSENGER also revealed the planet's composition, showing an abundance of volatile elements such as sulfur and potassium, challenging existing models of planetary formation that predicted a depletion of such materials in a planet so close to the Sun. Building on the successes of Mariner 10 and MESSENGER, the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA, collaborated on the BepiColombo mission, launched in 2018. Comprising 2 orbiters, the Mercury Planetary Orbiter and the Mercury Magnetospheric Orbiter, BepiColombo is designed to provide a more comprehensive understanding of Mercury's surface, interior, magnetosphere, and exosphere. After a complex journey involving gravity-assist maneuvers around Earth, Venus, and Mercury itself, BepiColombo is set to enter Mercury's orbit in 2025, promising to deliver a wealth of data that will refine our knowledge of the planet's origin, evolution, and current state. This mission represents the culmination of decades of technological and scientific advancements, incorporating cutting-edge instruments capable of operating in Mercury's extreme environment. The exploration of Mercury has not only advanced our understanding of the planet itself, but also provided broader insights into planetary science, including the processes of planetary differentiation, the generation of magnetic fields, and the evolution of terrestrial planets. Mercury's unique characteristics, its oversized metallic core, its magnetic field, and its extreme temperature fluctuations, serve as natural laboratories for testing theories about planetary formation and evolution. Additionally, the challenges of exploring Mercury have driven innovation in spacecraft design, navigation, and materials science, with technologies developed for Mercury missions influencing broader applications in space exploration. As BepiColombo continues its journey and future missions are proposed, the exploration of Mercury remains a testament to human ingenuity and curiosity, offering profound insights into the mysteries of our solar system and the fundamental processes that shape planetary bodies. Through decades of exploration, Mercury has transitioned from a distant point of light in the night sky to a richly detailed world, contributing to our understanding of the cosmos and inspiring future generations to explore the unknown. Future exploration of Mercury, the innermost planet of the solar system, poses an array of formidable challenges that reflect its unique position, extreme environment, and the technological limitations of current and near-future space exploration capabilities. The most prominent difficulty arises from Mercury's close proximity to the Sun, which subjects any spacecraft attempting to approach it to intense solar radiation, searing heat, and the gravitational pull of the Sun. These factors create a thermal and gravitational gauntlet that makes reaching Mercury a far more complex task compared to missions to the outer planets or even Venus and Mars. Spacecraft must undertake intricate trajectories involving multiple gravity assist maneuvers around Earth, Venus, and Mercury itself to gradually reduce their speed and align with Mercury's orbit, requiring years of travel before even arriving at the planet. Once there, spacecraft must endure surface temperatures on Mercury that range from a scorching 430 degrees Celsius, 800 degrees Fahrenheit, during the day to a frigid minus 180 degrees Celsius, minus 290 degrees Fahrenheit, at night, posing severe challenges for thermal regulation and material durability. Building spacecraft capable of withstanding these extreme temperature fluctuations and operating efficiently in such an environment necessitates the development of cutting-edge insulation, heat-resistant materials, and advanced cooling systems. In addition to thermal challenges, Mercury's lack of a substantial atmosphere means that spacecraft cannot rely on atmospheric braking or aerodynamics to slow down during orbital insertion, as is done for Mars or Venus missions. Instead, missions to Mercury must carry large amounts of fuel for propulsion, significantly increasing mission costs and complexity. This lack of atmosphere also contributes to the challenges of surface exploration. Unlike Mars, where parachutes and atmospheric drag can assist in landing, any lander on Mercury would need a highly controlled and fuel-intensive descent, compounded by the planet's weak but non-negligible gravity. Once on the surface, a lander would face prolonged exposure to harsh solar radiation and a complete lack of atmospheric protection, requiring robust shielding and energy systems capable of enduring Mercury's inhospitable conditions. Moreover, the long Mercurian day, lasting approximately 176 Earth days, means that solar-powered systems would face challenges in surviving the extended night period, necessitating innovative energy storage solutions or alternative power sources, such as radioisotope thermoelectric generators, RTGs, which are expensive and limited in availability. Another major obstacle for future exploration lies in the difficulty of studying Mercury's geological and geophysical features in greater detail. While orbiters like NASA's MESSENGER and ESA-JAXA's BepiColombo have provided valuable data, key questions about Mercury's interior, such as the precise composition and state of its core, the dynamics of its weak but global magnetic field, and the processes driving its contraction and tectonic activity, remain unanswered. Addressing these questions requires advanced instruments capable of high-resolution imaging, seismic sensing, and magnetic field analysis, all of which must operate reliably in Mercury's extreme environment. Similarly, exploring Mercury's polar regions, where water ice deposits have been detected in permanently shadowed craters, poses unique challenges. These regions are some of the coldest places in the solar system, contrasting starkly with the planet's otherwise scorching temperatures, requiring spacecraft and instruments that can handle rapid and extreme temperature variations within short distances. Furthermore, Mercury's exploration is constrained by the immense costs and risks associated with missions to such a challenging environment. Developing and launching spacecraft capable of reaching and operating around Mercury requires significant investments in technology, fuel, and infrastructure. The long mission timelines, often spanning decades from conception to data return, also present logistical and financial hurdles, making it difficult to sustain momentum and funding over extended periods. In addition to technical and financial challenges, Mercury exploration faces competition from other priorities in planetary science, such as missions to Mars, the icy moons of the outer planets, or exoplanet studies, which may offer more immediate scientific returns or broader public interest. Despite these challenges, Mercury remains an essential target for exploration due to its unique role in understanding the formation and evolution of terrestrial planets. Its oversized metallic core, ancient surface, and extreme environment provide a natural laboratory for studying processes like core differentiation, magnetosphere generation, and the effects of proximity to a star on planetary evolution. Overcoming the challenges of Mercury exploration will require Mercury, the smallest and innermost planet in the solar system, is full of fascinating fun facts and intriguing comparisons that make it a unique world, standing apart from its planetary neighbors in many ways. To start, Mercury is the fastest planet, zipping around the Sun in just 88 Earth days, which gives it the shortest orbital period of all the planets, earning it the nickname the Swift Planet. Despite its quick orbit, Mercury rotates on its axis incredibly slowly, taking 59 Earth days to complete a single rotation, resulting in a single solar day, sunrise to sunrise, that spans an astonishing 176 Earth days, longer than its entire year. This slow rotation and fast orbit create peculiar effects, such as the Sun appearing to rise, pause, and briefly reverse direction in the sky at certain points on Mercury's surface. Comparatively, Mercury's surface is a harsh and extreme environment, experiencing the most significant temperature variations in the solar system, with blistering daytime highs of 430 degrees Celsius, 800 degrees Fahrenheit, and bone-chilling nighttime lows of minus 180 degrees Celsius, minus 290 degrees Fahrenheit. This stark contrast is due to Mercury's lack of a substantial atmosphere to retain heat, unlike Earth, where the atmosphere helps moderate temperatures. Mercury's size is another point of intrigue. It is only slightly larger than Earth's moon, with a diameter of about 4,880 kilometers, 3,032 miles. Yet, it is significantly denser, second only to Earth. This density is a result of its enormous metallic core, which makes up about 85% of the planet's radius, a far greater proportion than any other planet in the solar system. Interestingly, if you were standing on Mercury, you would weigh only about 38% of your Earth weight due to its lower gravity. Despite being so small, Mercury has a magnetic field, an unusual feature for a planet of its size. However, this magnetic field is much weaker than Earth's, and its origin is believed to be tied to the dynamo effect generated by its partially molten core. Mercury's surface, covered with craters, cliffs, and plains, tells the story of a geologically ancient world. Its surface is heavily cratered, much like the Moon's, with some features like the Caloris Basin, a massive impact crater over 1,550 kilometers, 960 miles, in diameter, standing out as evidence of a tumultuous past shaped by asteroid and comet impacts billions of years ago. When it comes to polar regions, Mercury surprises us again. Despite its proximity to the Sun, its poles harbor water ice in permanently shadowed craters, where sunlight never reaches. This discovery, made by radar observations and confirmed by the MESSENGER mission, challenges assumptions about where water can persist in the solar system. Mercury also has a tenuous and dynamic exosphere made up of atoms like sodium, magnesium, and calcium, which are ejected from its surface by solar wind and micrometeoroid impacts, creating a faint, constantly changing envelope of particles around the planet. Comparatively, Mercury lacks moons or rings, unlike the other terrestrial planets and the gas giants, due to its weak gravity and the Sun's overwhelming tidal forces, which would disrupt any attempt to sustain such features. From a cultural perspective, Mercury has been known to humans since ancient times and is one of the 5 classical planets visible to the naked eye. It was observed by civilizations such as the Babylonians, who called it Nebu, and the Greeks, who referred to it as Hermes when it appeared in the evening and Apollo when it appeared in the morning, reflecting its fleeting visibility. In Roman mythology, it was associated with the swift messenger god Mercury, a fitting name for the fastest-moving planet. Comparatively, modern science has added layers of intrigue to Mercury through exploration, with missions like Mariner 10 and Messenger revealing its geological, chemical, and magnetic complexities. The upcoming BepiColombo mission promises to deepen our understanding further. Despite its challenges, Mercury remains an object of wonder, from its dazzling speed and extreme conditions to its surprising capacity to harbor frozen water and its crucial role in validating Einstein's theory of general relativity through the observed precession of its orbit. This tiny, fiery world, closest to the Sun, yet holding so many secrets, continues to captivate our imagination, offering endless comparisons to other planets and serving as a reminder of the diversity and richness of our solar system. Thank you for exploring the fascinating world of Mercury with us. We hope you enjoyed diving into the mysteries of the smallest and swiftest planet in our solar system, learning about its scorching days, freezing nights, enormous metallic core, and incredible history of exploration. From its extreme temperature swings to its role in validating Einstein's theory of relativity, Mercury proves that even the tiniest planet can have an outsized impact on our understanding of the cosmos. If you found this journey through the innermost planet of our solar system as exciting as we did, we'd love for you to join us for more adventures into the wonders of the universe. Don't forget to give this video a big thumbs up. It helps us know you're enjoying our content and motivates us to keep creating more. If you haven't already, hit that subscribe button and turn on the notification bell so you never miss another deep dive into the amazing worlds of our solar system, fascinating scientific phenomena, or the mysteries of outer space. Your support means the world to us, and by subscribing, you're joining a growing community of curious minds and space enthusiasts just like you. We'd also love to hear your thoughts. What was your favorite fact about Mercury? Is there a topic you'd like us to cover in the future? Drop your ideas and questions in the comments below. We're always excited to connect with you and explore the universe together. And if you know someone who would love learning about Mercury, share this video with them. It's a great way to spread the excitement of space exploration and discovery. Thank you for watching, and until next time, keep looking up at the stars and wondering about the incredible mysteries waiting to be uncovered. See you in the next video.
Welcome kids to Learning Land. Grab your dreams and take a stand. Colors, numbers, letters too. Adventures here for me and you. Let's explore and have some fun. Count to 10, it's just begun. Sing and dance across the screen. In Learning Land we'll be a team. Learning is a magic ride. Come aboard, let's learn with pride. Shapes and stories, games to play.